여러분 안녕하세요. This is chapter 7, part 1. In this chapter, we are going to talk about dopant diffusion. So why do we want to discuss dopant diffusion? So it's very important to accurately control the placement of the active doping regions. So we care about the concentration and the location of the active dopant because the doping profile determines many important features in the transistor. For example, if you look at a typical planar transistors, it has actually pretty complicated doping profile, as you can see from this figure on your left. And basically, we want these type of profiles so that we can improve the performance of the transistor. And also, the doping profile also determines many parasitic resistances and capacitances. So this is not intended, but this is something you cannot avoid in your transistor. So for example, the figure on your right shows a lot of parasitic resistances, which is coming from the contact and the source itself, etc. So these type of parasitic resistances also have some large impact on your transistor performance. So the doping profile will determine a lot of these parasitic resistances and capacitances. So if we can, we want to control the doping profile so that we can optimize the performance of the transistor. So if you look at this table from ITRS, there are a lot of parameters or requirements they specify for different year to maintain the performance of the transistor while we scale down according to Moore's law. So for example, if you look at this row, it says source drain extension abruptness, meaning how fast the doping profile drops abruptly. And you can see that it's decreasing. So you have only 2.8 nanometer for 10x decrease in the doping concentration. And also, you also want to control the depth of this extension for source and drain. And you can see that it's also decreasing, right? It's around 100 nanometer, but it was expected to be 5.1 nanometer in 2018. So you can see that these doping profiles are changing, and it's becoming more challenging to achieve these requirements or specifications. So in general, we want more precise control on the doping profile. So now we know that the junction profile is very important. So how do we measure the junction profile? So this is one way to estimate the junction profile, especially if it's uniform and perfectly abrupt. Um, but in reality, most of the junctions are not uniform. We will see why this is the case in later slides. But for now, let's assume that it's uniform and it's abrupt. Then what you can do is you can measure the resistivity of that uniform junction. Um, so let's say this red region is doped region with a certain doping concentration, uniform concentration. What that means is that you will get a constant carrier density, and then it needs to be multiplied by Q, which is the amount of charge per carrier, and also the velocity of the carrier that will give you the current density, say. And then this V can be expanded to mu times E, where mu is the mobility and E is the electric field. And basically this is the equation for the resistivity, which relates the current density to the electric field. So you can find out from this equation what the resistivity is from the carrier density, which will give you the information about the doping concentration. Um, and also, in reality, what you usually measure is the sheet resistance. Um, so the sheet resistance is basically this one. You divide the resistivity from above by the thickness of the junction, which is Xj in this case, and that's called a sheet resistance. So at the end, your resistance of your structure will be given by this equation, right? This is coming from the dimensions of that region, doped region, and the resistivity, and or you could use the sheet resistivity and then the dimension of the doped region. So either resistance or the sheet resistance is something you can measure from your structure. Therefore, from there, if you know the dimensions, you can estimate the resistivity, and then that will give you some information about the carrier density or the doping concentration. So you can actually use two different carriers, electrons and holes. Usually in the doped silicon, only one of them one of them will be much larger than the other, so only one term um, remains, but this is kind of full equation, which we briefly discussed in chapter 1. So again, what if it's not uniform? So that's on the next slide. So if it's not uniform along the depth, so the concentration of dopant is changing with the depth, and what you can do is actually you can see this as a kind of a parallel resistance in parallel. So if you look at these, for these small regions, they have uniform concentrations if you make this really small enough. So what that means is you can just integrate the doping concentration. So in general, the mobility itself might change with the doping concentration as well. So this is kind of an equation you can use to integrate um, uh, the resistivity of the entire structure using integration. So this is background doping concentration. If you have the background dopants. So there are kind of other ways to measure it, because right, this is still kind of gives you the resistivity information once you know the concentration is a function of depth. But just by measuring the resistance, it's not gonna give you this. The concentration is a function of depth. So is there any other way to actually measure the concentration as a function of depth? There are a couple of ways to measure that. They are not perfect, but they give you more information about the doping profile. The first one is something called SIMS, or secondary ion mass spectroscopy. So the reason why it's called secondary is because there's a primary ion and secondary ion. Um, so the primary ion is a kind of a very energetic ion which is generated by this ion gun. So this is not within your sample, but they go to sample with pretty high energy. And then this is your sample. You want to know the doping concentration in the sample. And what happens is that this energetic primary beam, or the ion beam, will sputter the atoms off from the surface of the sample. So that will generate this secondary ion. So this will contain the dopants. So if it is a silicon, if it's doped in your secondary ion, you will get silicon atoms and also dopant atoms or ions as well. And they will have different mass. So that's why we put mass in here. And you can use some kind of mass analyzer, right? Because if their mass is different, for a given force, their radius will be different. So you could come up with some kind of mass analyzer, and then using the detector, you can count the number of dopants per number of silicons. So that will give you the concentration of dopants. And also, since you are kind of etching, you are removing the material from the sample, as you do this more and more, it will go deep into the sample. So if your doping concentration is not constant, it will change with time or depth within the sample. So using this SIMS technique, you can uh, figure out the doping concentration as a function of depth. Another way to measure the doping profile is something called spreading R measurements. So here, this is your sample, but what you do here, you create some slope like this, and then you measure the sheet resistance um, along the surface, and then as you go deeper, or as you slide down along this uh, slope, you will get a different resistance value, resistance, which means that it kind of gives you some convoluted information about the doping profile along the depths. So you need to reanalyze the data after the measurements, but this is kind of one way to measure the doping profile. But this is kind of destructive. This is destructive, right? So you cannot use this for all the samples you have. But from time to time, you could do something like this to figure out the doping profile. And also, we talked about the CV measurements. So the same CV technique that we discussed in chapter 6 can be used to extract the doping concentration information as well. And also, you can actually use some TM techniques. So you could cut the wafer to get the cross section, and it's not going to give you the exact concentration, but you can see that there's some kind of clear differences. So you can at least measure the depth of the junction using these imaging techniques as well. So on the next few slides, what we want to do is actually model or derive the mathematical expressions for diffusion or the doping profile. So let's talk about the diffusion. So it's some basic concept you already know. So if you have a region where high concentration of certain mobile species exist, and if you usually at higher temperature, they will diffuse to this empty region, and then eventually, if you just wait long enough, it will distribute uniformly within the structure. So this is a diffusion process. So usually when you form the junction in the silicon or semiconductor, we follow two steps. Sometimes these two steps are not well separated, but we can kind of call them as a two-step process. So in the first step, it's called pre-deposition. And then what you do is you basically create the small region where you have a high concentration of the dopants or impurity atoms. So in this case, this is an example. You could put the whole wafer in the chamber. So similar to um, silicon oxide thermal oxidation, this gas will penetrate into the silicon, especially at the surface. So this dopant, if you put the wafer in the dopant gas chamber, the dopant atoms will kind of penetrate into the silicon like this. So that's called something called pre-deposition. Um, and sometimes this doesn't have to be a gas. It can be even a solid. You can deposit actual physical layer with a lot of dopant atoms, and then they will penetrate into the silicon as well. So that's first step, pre-deposition. And then in the second step, you do something called drive-in. So again, usually at high temperature, you let them diffuse. So they will diffuse and form these junctions. And this drive-in actually activates the dopants as well, which we'll discuss more in detail in next chapter, chapter 8. So what we want to model is this drive-in. Uh, what's the kind of mathematical expression we can use to describe uh, the doping concentration or doping profile after the drive-in? Um, so let's take a more closer look at the pre-deposition. So the purpose is we want to introduce the dopants or impurity atoms, but we want to control the number of the dopants, right? Otherwise, it's going to be difficult to form the junction I want. So you want to control the number of atoms. So there are various methods. So as we just discussed, it can be a solid phase. So maybe you can deposit some glass layer with a lot of dopants, then they will diffuse into the silicon. And as we just discussed, it can be a gas. Right? These are typical gases with dopants, boron, phosphorus, arsenic. And we will talk about the ion implantation in chapter 8. And we already talked about it briefly in chapter 2. So we could use ion implantation as well. As you already know, ion implantation is dominant doping method because it has advantages. So for example, it can be a room temperature process, so you don't need high temperature. And then you can control the dose very precisely. And then it has a pretty large range. And then we will see more details why this is the case, but you can also control the depth pretty accurately by controlling the energy of these dopants during ion implantations. But the problem is the damage. We talked about these damages. A lot of damages creating dislocations, and damage will enhance the diffusion. And we talked about the channeling effect as well. That was also from the Q&A that we had. So it has certain problems, and but compared to the solid and gas phase, this is still better. So for solid and gas phase diffusion, no damage. That's the big advantage, and also the batch fabrication. So just like thermal oxidation, you can put maybe hundreds of wafers in one chamber, and they will get this solid gas phase diffusion at the same time. So that's what we mean by batch. So it's low cost process. However, the big problem with the solid gas phase diffusion is that it's not easy to control the dose. So usually you have to just wait until it saturates. So what that means is that your concentration will be always the same, and it will be the solid solubility will be the same as the solid solubility. What that means is that the solid solubility is pretty high, So it's difficult to get a low concentrations. So ion implantation, you can choose to have really low dose if you want, but for the solid and gas phase diffusion, uh, achieving the low concentration or low dose is not easy. So now let's look at the step 2, uh, the driving step or the actual diffusion step. Sorry, so there's actually one more slide before we go to the actual drive, the diffusion steps. Um, so since we talked about the solid solubility a lot, there's more details on this slide. So the solid solubility is basically it's the maximum concentration you will get if you just wait long enough. So that's kind of a thermodynamic equilibrium for the concentration of dopants. And this is the solid solubility. It's a function of temperature for famous dopants and other species, silicon. And eventually, if you put more than the solid solubility, they will precipitate, which is bad when it comes to the junction, right? We don't want the dopants to form a region where we don't have any silicon, but only dopants. So again, for solid and gas phase, this is basically what you have to reach to form a reproducible junctions. Because if you just the only way you can get the reproducible junction is to get to the maximum where it's kind of self-limiting. It's limited by itself, so it's not controlled by the time. You just wait long enough, and then you will get that concentration, which is probably too high, and that's not good for IC manufacturing. So we use ion implantation. Um, so we talked about the solute solubility, but also something we want to talk about now is the solute solubility is not same as the electrical solute solubility. So what do we mean by this electrical solute solubility? Uh, so the reason, the purpose why we want to have these dopants is because they can give you some carriers like electrons or holes. So if you think about the arsenic, what they do is they ionize in the silicon when they doped into silicon, and then they basically release one electron because when it forms the bond with silicon, so this arsenic is pretending as if it's a silicon, so it will form the bond with the silicon, and it has one excess electron, so which becomes a free carrier. This becomes free, released. This is not tied to arsenic anymore, arsenic atom anymore. So you create the free electron. So in this case, that means this is electrically active. Uh, However, if you have too much arsenic, so they are still within a solid solubility, so to speak. So they kind of replace the silicons. But if you have too much arsenic, too many arsenic, what can happen is that uh, you can create some vacancies in here, and then they will just kind of maintain these two additional two electrons like this, and then they don't, since it's not bonding with the silicon because there's no silicon in this vacancy, they don't need to release this electron, right? So in this case they are inactive. So uh, and there's no reason to dope like this because the purpose of doping is to create the free carriers, but they are not contributing any free carriers. So usually the solid solubility is larger than electrical solubility. So uh, this is kind of too high. The solid solubility is too high. And then there's no reason to dope the silicon with this much concentration. Um, So now diffusion. So there are equations we need to know, and I believe these are equations you already know. So the first one is Fick's first law. So this kind of defines the flux. So if you have a difference in concentration as a function of location or distance, how many atoms move per area and per unit time, um, and that's basically given by this Fick's first law. So it will be proportional to the slope of this concentration gradient, and then it gets multiplied by the diffusivity, which is the material parameter. Um, so it's pretty simple equation, and you need have a minus sign in here because uh, if the concentration is high, uh, then you lose those atoms from the region with high concentrations. You need to put the minus sign. But we need another law, because what we actually want to know is the shape of this one after a certain time, right? So let's say you started from here at T1, but after a certain time it became T2, and then they will kind of become more smooth like this. But what you want to know is not just the flux, but this impact of the flux, which forms the doping concentration profile like these. And to figure that out, you need to know how fast this doping concentration is going up or going down. Right here, it's going up, and it's going down here. So you want to know how to model this behavior, which will be a function of time. So that's Fick's second law, right? So it kind of tells you the change of the concentration at a given location as a function of time. Um, and the equation is basically this one. So there's a second derivative. So the left one is the partial derivative with respect to the time, is t, but the term on your right is the second derivative with respect to x, which is location. Right? So the Fick's second law is somewhat more complicated because now you have two variables, t and x. But still, this is kind of simple enough so that you can solve them analytically using your mathematical skills with certain boundary conditions. So we are going to look at some of the famous analytical solutions of this Fick's law. And for just like any other PDE, partial differential equations, you need a boundary conditions or initial conditions as well. Uh, so depending on what kind of boundary and initial condition you have, there are 4 different cases. There can be more, but we are going to look at these 4 cases. These are kind of brief explanation for each, but we will explain these later in each slide. So the first case is something called limited source in medium. So it's limited, meaning you put a certain amount, but you never add more later on. So you are always, the total amount of those will be fixed in your whole structure or medium. So that's what we mean by the limited source. And it's in medium, meaning this is kind of infinite. This is kind of infinite medium, but in the middle or somewhere in the medium, this dose is kind of concentrated at the beginning. So mathematically, this will be some kind of delta function, right? Because they only exist at 0. If you go a little bit smaller or larger in x, there will be no dopant at time 0. And there is actually very good mathematical solution for this. So with this boundary and the initial condition, you need to solve this, which is Fick's second law, and this is the solution for this equation. So you can verify if we just put this thing in here for C, and then find this time derivative and the x derivative, partial derivative, you can show that this holds if you use this solution. And if you take a look, basically this is kind of Gaussian function, Gaussian constant distribution, right? So there's an exponential function, and then we set this starting point as 0, and then it will be symmetric as expected. So this is kind of a shape of this Gaussian profile at different time. And this is the linear scale for concentration, and this is the log scale for the concentration. So they will spread, and what you see is that your peak should drop. Right? Your peak should drop, and right, this tells you the peak, right? Because exponential function will be 1 when x is 0, right? So this will specify the peak. Your dose is fixed, right? That's limited source. So the peak height will be determined by this term t in here, right? So they will decrease like this. And then there's something we define as a diffusion distance, and that's basically coming from here, right? So if you rewrite this, you can kind of write this as a like this, and then basically this is the length, it has the unit of a length, so this should have the unit of a length as well. So actually if you use the same value for this, that means it's kind of identical, right? If you use the same value for the whole thing, so what that means is that that's kind of this thing can be called as diffusion distance, which will increase with time, so it has t in it, right? So so you can see that you can kind of explain this different. So if you normalize it, and then you can kind of see how wide the profile is relative to its peak, and then this will be proportional to this term diffusion distance. So now we are going to look at the case number 2. So the only difference now is at surface instead of in medium. So this is a case. So in this case, there's nothing. This is maybe air when x is smaller than 0, but the medium is infinite and it's in here. You're maybe silicon. But what happened here is that you have this delta function at the surface, but you don't add more dose, so that's still limited, but you let them diffuse. So in this case, since this is air, there's no diffusion to this junction. So how do we solve this? It turns out you don't have to solve this again. You can just use the solution from the previous case, which is limited source in medium, and just use it for this one. So what we are going to do is we are going to just create the imaginary limited source on the other side, right? So this is the line, and then you just add the same amount of dose on the left side of this one. So this is kind of two delta functions side by side, and then you just change this to a the limited source in medium problem. And what's going to happen is that there's 2q because you added q in here, but if you just cut them in half, the half on the left will diffuse to the left side, and the half on the right will diffuse to the right side, and there will be no diffusion between these two boundaries. So there's no diffusion to the other side. So that kind of satisfies that the condition that we talked about at the beginning. There's no diffusion into the air or empty space. So just solve this limited source medium problem with 2q, but you just ignore the solution on the left side. Just use the solution from the right side, and that's going to be your solution for this second case. So basically, the equation will be the same. So this was So this is the equation for 2q for the limited source in medium, right? So you just basically take um, the, the right half uh, of this equation. So you can see that there's no 2 anymore because they canceled out. So this is the solution, which is still the Gaussian profile. So this was simple if you know the first case. So the third case is something called infinite. It's not limited anymore. It's infinite internal source in medium, right? So this is the same phrase we used for the first case in medium. Um, so the medium is kind of infinite, and the amount dopant is infinite. That's because this is the initial concentration for the dopants, and you can see that the medium is and it's constant uh, initially when the x is smaller than 0. So in this region, you have a constant concentration, but it's a infinite depth. So that's why it's infinite internal source. So there's an infinite amount of dopants. Um, and what's going to happen is that if you just wait long, it will diffuse to the right. So it will form something like this. So we want to know the shape of this curve, this diffused work profile. And one way to solve this problem is you can treat this infinite source as the sum of these small bars. And if you look at this small bar, if you fix this delta x, the dose is the C, the concentration times delta x. So this dose is fixed. So if you just look at this one small region, it's exactly the same as um, the limited source in median problem, right? So and you can use the superposition principle um, to combine the contributions from all these small pieces. So this is kind of the idea. So here, if you actually use this kind of fixed amount delta x, you can use this delta function, right? So this is the same profile that we talked about in previous cases, the Gaussian profile. But now your dose has a c times uh, delta x. And then also, if you look at this x location, right, the distance between this xi and x will be changing depending on which piece you use, right? This guy will have different distance, right? So that's why you get this x minus xi to account for this difference in the distance. Um, but eventually what you want to do is to change this to a actual integration, right? So if you make this delta x is really small, you can change this to dx or d alpha in this case, because there's x already. Let's use d alpha. Um, and so what you are doing is that, so now this is kind of a, right? And a changed from 0 to minus infinity, right? So that's that. And that's the distance between this bar, small bar, and the actual location where you want to know the concentration. And this is exactly the same equation that we talked about for Gaussian profile. And you can actually do the integration of this thing using this definition for the error function. So error function is something fairly useful. So this is kind of mathematical definition for error function. And you can rewrite the equation like this. So this is the equation, right? So this is error function, and or you can use the complementary error function. 1 minus error function is complementary error function. And then the shape will look like this. So one interesting feature of this complementary error function, right? This is the same equation, and it's basically symmetric. So can see that the symmetry in here and along this point. So they always cross this point. So this point, the concentration at this point is fixed. It's always 0.5, half of the original concentration. But basically this much of dopants move to here, and then you're getting more as time passes. So let's talk about the first case, which is the same infinite source, but now it's not in medium, but at a surface. So first we want to talk about why we get an infinite source at surface. How is that possible? So for some reason. So if you remember the solid and gas phase diffusion, um, so we basically have infinite source uh, in the air or in the solid because it has really high concentration for dopants. So the concentration at the surface will be maintained at the solubility limit. Right? If you wait long enough, they will reach the solubility limit, but it will never go higher than that. And also in lecture 6, we talked about Henry's rule for gas phase. So it's a kind of similar concept. For a given pressure, you will get some equilibrium concentration at the surface as well. So that's how you get maintain certain constant surface concentration, because outside of the surface you have some kind of infinite source which helps you to maintain the maximum concentration at the surface. So anyway, so if we have the infinite source at surface, what's going to happen? And again, we are going to use the previous solution. So if you look at the solution from the previous page, this is the solution from the previous page, this figure. We already talked about that. There's one point here where the concentration never changes. It's always C over 2. So the concentration doesn't change. So uh, basically it's giving you a constant surface concentration, just like we discussed. So we already know the solution. If you know the solution from case number 3, so this was the solution, and now you just need to modify this to be C over 2, and then you can integrate. Uh, so the dose will increase with time, right? Because previously in case number 3, you were just moving those dopants from here to here, but now you're actually adding dopants in the silicon, so the dose will increase with time. So you need to integrate uh, the dose with x times dx. Dx is mixing, and then this integration will give you this one. So this will be the dose you are getting in the structure or silicon. Um, so the first two cases were limited source, which means the infinite dose. Um, the case number 3 and 4 was infinite source. So for infinite source problems, we got error function curves. So that corresponds to those gas or solid phase diffusion. But the fixed source dose is more like a Gaussian. It gives you Gaussian, and it comes from the ion implantation, because when you do ion implantation, you determine the amount of dose you put in, and then let them diffuse later on at high temperature. Um, so again, as we just talked about, the error function, the dose will increase with time, but the Gaussian profile, your peak concentration will come down with time. So if you actually get the total dose, it will be constant because you have limited source. So let's talk a little bit more about these dopant diffusion coefficients. And we are going to say intrinsic because there will be a lot of secondary effects like electric fields, defect density, and so forth later on in part 2. So for now, this is intrinsic. When everything is perfect, or when we ignore all the secondary effects, we will get this intrinsic dopant diffusion coefficients. And then it turns out if you measure, they follow this Arrhenius behavior, just like any other processes. So it depends on temperature a lot because it's exponential function. And then you need to know the activation energy for EA. And then as a result, you can see that the diffusivity in the log scale will change a lot. Right? This is almost a million times bigger as a function of different temperature. So another thing we want to talk about is the effect of successive diffusions. So the question here, what if you change the temperature during diffusion? And you already know from chapter 2 that this is happening, right? Because after the ion implantation, you will go through many different annealing steps during the IC fabrications. So the temperature will be changing for each diffusion. And as we discussed before in the previous page, the temperature change will change diffusivity a lot, orders of magnitude, because it has exponential dependence. So it can be quite difficult to think about this problem, but actually if you look at these solutions, this is Gaussian, right, from case number 1 and 2, and the error function from 3 and 4. You can see that this diffusivity is always multiplied by T. Whenever the D shows up, it's multiplied by T. Like for example, like if you have some D in here, this is kind of random, but it's not multiplied T, it will become much more difficult to model. But whenever you have D in the equation, it always gets multiplied by T. So that's kind of a very easy way to model this thing, because you can just multiply these D and T for different temperatures or different time, and then add them up, right? Because after D1, T1, it's still Gaussian profile, so it doesn't matter how you got here, right? It's maybe it was D1, T1, or maybe it's same as D2, T2, right? So you can just replace this D1, T1 with D2, T2 at different temperature, and you will get the same profile anyway, because everything else is the same. Only different thing is DT. So what that means is that you can just treat this DT as some kind of effective value and then sum them up. And then it will give you one DT effective value for your final profile. So this is summary or review, right? There's a fixed first low, which is this, a very simple model. And there's a fixed second low, which is this. And using these, you can find the doping profiles, you can model or find the analytical expressions. So depending on your boundary and initial conditions, you could get the error functions, complementary error function, or the Gaussian functions. So far, it was relatively simple mathematically, but in part 2, it's going to become more complicated because we are going to discuss all the secondary factors on diffusion, such as electric field, variable diffusivity. So the diffusivity is not constant anymore. So if it's constant, it comes out of here. But if D changed with X, it will become more complicated. And also we talk about those defects, vacancies, and interstitials. And it's going to be more complicated. So At that point, we don't have any analytical solutions. We will have to use some numerical simulations to figure out. So that's it for this lecture. Um, if you have any questions, please let me know and talk to you next time.